Alright, so just going to finish off the problem on math space about what we can tell from the derivative, from the second derivative, sorry. As you remember, we had this function here, and we had to tell which of these options was correct. We already talked about the gradient, and we talked about the function. Now we have to ask, is there or isn't there a point of inflection? Okay, so to answer this question, you might have to watch the video on the basic example of how to find inflection points, which should be uploaded by now. It'll make a lot more sense if you have, but even if you haven't, let's just go through the steps. Now don't worry about actually doing these, we will do these together. So first step is we find the second derivative, we set whatever equation we get equal to 0, we solve that equation, then we calculate what the second derivative is for different values of x, and find where that second derivative goes from negative to positive around those values of x, that is. Then if we find that's true, then we can plug that back in to step 2 to find the y coordinate, and then repeat again if we have more than one x value. Like I said, obviously this is not going to make much sense unless you watch the other video, so if it doesn't, then probably best to watch it as well. But anyway, let's come to look at this problem, because here our function is 2x squared minus 3x plus 4. We found the first derivative was 4x minus 3, and the second derivative was 4. Okay. And how we do that? We just basically derive everything. So derive the first term like so, and then the second term, and then the third term, and that's how we got the first derivative, and did the same thing for the second derivative. Sorry, this one here. Okay? Now, this is the next step in trying to find whether there is an inflection point or not. It is to set the second derivative equal to 0 and solve the resulting equation. But here's a problem. This is our second derivative. This is what it looks like when we set it equal to 0. Well, obviously this doesn't make any sense, because how are we going to, this is not even an equation really. How are we going to solve it? Well, just based on this, we can say there is no point of inflection. Okay, and you can probably say this to your teacher or in the exam that I've followed the algorithm, and it shows that I can't find an inflection point. So at this point you can actually stop the video if you wanted to, but if you wanted to understand what this meant, and that might be useful if the teacher asks you to explain why that result that we got, which is this one here, 4 is equal to 0, why this problem means that we can't find an inflection point. If you want to know how that works, well, keep watching, because what I'm going to do first is I'm just going to run through the condition again about for there to be an inflection point. Now you might remember this from the previous video on inflection points and on the basic example as well, that the condition that we have, that the condition for a function, whatever it might be, to have an inflection point is that the second derivative of that function must go from positive to negative, or vice versa. So somewhere along that function, its second derivative must go from positive to negative, or negative to positive. Okay, so what does that mean really? Well, what that means is, and this is probably a bit abstract, it'll make more sense when you look at the graph, but the abstract version of this is that remember, the second derivative must go from positive to negative, which means that the change in the first derivative, remembering that derivative means change of something, so the change in the first derivative must increase and then decrease. That's what this means in an abstract form. But we'll explain it to you with a graph, because that'll make a lot more sense. And what that basically means, in a bit more of an intuitive sense, is the steepness or the gradient of the tangent to the function, okay, has to increase and then decrease, or decrease and then increase. I'm just going to open up this animation here. Okay, so here's the curve of our function. Let me see where it is. Yep. This is the curve of the function that we're dealing with. That's 2x squared minus 3x plus 4. Now, ignore all this stuff, by the way. Just focus on the graph here. This I'm going to show you is the tangent to the function at some random point. And as you might remember from the previous video on what inflection points are, we can obviously pick different points. It doesn't really matter. What's more important to notice is how the tangent changes as we change the point that we choose. Okay? And you might remember from the previous video that what we're looking for is for the tangent to go from below the curve to above the curve. As you can notice here, that doesn't happen. You start off all the way on the left here. I'll zoom out a little bit so it makes more sense. As you can see, the tangent just sits below the curve here. Even if I change it, it just keeps sitting below the curve. So it doesn't ever actually transition from being above the curve to below the curve, or below the curve to being above the curve. Okay? You're probably wondering, how does this relate to what we talked about before about start from here again, about, you know, the change in the first derivative being must increase and then decrease, or the steepness of the gradient. Well, let me show you. So we've graphed it. As you saw before in the animation, the tangent could sit anywhere along the curve. We picked this random point here just for the point of illustrating what I was talking about. What you'll notice is the steepness of this tangent is negative. It's pointing down, right? That means the steepness is negative, or it has a negative gradient. Okay, and then as we moved along the curve, you saw that the steepness, the tangent, sorry, started sloping up, which means that the steepness has actually become positive. So what does that mean? If you started off with a negative value, like a negative gradient, started over here. Okay, you started off pointing down. You started with a negative gradient, a negative number for the gradient, a negative number for the steepness, if you will, and then we went to a positive number for the steepness. What do you think happened? How did that happen? Well, how did that happen? Sorry. The only way that could have happened was that the gradient was just constantly increased, right? And what did we see before? We saw that the second derivative was a constant positive number, positive 4. That was what the second derivative was. So that means that the gradient increased constantly by positive 4, and that's how it changes as it moves along. Okay? But coming back to the relevant point about inflection points, we needed that condition that the gradient increased and then decreased, or the opposite. And as you can see, it hasn't done that. Right? It's just constantly increasing, getting steeper and steeper, getting more positive steepness, I should say. Not steeper, but getting more positive steepness. Right? Yeah, so that's why you can't have an inflection point. Now, before I move on, I want to show you from the previous video an example of the function that does have an inflection point. You might remember this from the previous video. Okay, so this is a different function. Don't worry what it is. This is just for the purposes of illustrating what an inflection point is. And like we did before, I'm going to show you the tangent here, which is in orange over here. So bring it over here. Okay. So at this point, as you notice, the tangent's sloping upward, and then it goes and it slopes downward, and then while it's sloping downward, it transitions back again to sloping upward. Okay, so just see that again. Started pointing up, then down, from down back to up. Okay, coming back to the presentation. Skip all this. Sorry. So this is just some pictures of what we just saw. This is the function and the tangent, obviously, as you can see, sloping up. What we know what that means. It means that it has a positive gradient. And then we saw it sloping down, which means that it has a negative gradient. So what just happened there? The gradient decreased because we started off with a positive number, positive gradient, positive value for the steepness, and then we went to a negative value for the steepness, or negative gradient. So we had to subtract some number, right? We had to have a the change in the gradient had to be a negative number, right? So that means the gradient has decreased, right? But then, this is the more important part, so continuing from there, and then what happened was we had a negative gradient, whoops, this one here, that then changed back to being a positive gradient. So the gradient increased, right? The gradient was added to by a positive number and it increased. What does that mean? It means the gradient decreased and then it increased. So the gradient was positive here, it decreased down to the negative gradient here, and then it increased up to the positive gradient here again. And that's why we can say that this is rough, obviously, but this is roughly where our inflection point would be.